So we are going to kick off this series by revisiting the concept of a category and extending it in certain ways. So we are going to be enriching categories. First, recall a category C consists of objects and morphisms, meaning that there is a class of objects, and for every two objects, x and y, in C, the set of morphisms, well, I just said it, is a set, nothing more, and we have a map called composition going from, well, for every object x, y, and z, going from the morphisms from y to z, Cartesian product with morphisms from x to y, to the morphisms from x to z, such that this operation is associative. And in addition, for every object x, we also have a distinguished morphism from x to x. We have, it's called the identity on x, is a morphism from x to x, such that pre and post composition with the identity doesn't change the other morphism. Meaning that, well, f composed with the identity is just f, and the identity composed with f is f, where we here take id to be the identity of the only space, such that we can compose the two. But if we actually go out into the world and study categories, we find that a lot of categories actually have more structure than that. Because, I mean, requiring that these sets of morphisms just be sets isn't really much. And yeah, usually we find that they have more structure. For example, in the categories of abelian groups, or of k-vector spaces, or of k-algebras, or modules over some ring, we find that the space of morphisms between two objects is actually not just a set, but an abelian group. Meaning that we can compose morphisms, but we can also add and subtract them. So it seems useful to define a particular kind of category, and that is what we are going to do. So a category C is called abelian if for every two objects x and y, the set morphisms in C from x to y is an abelian group. Usually written with addition and 0. And if the composition from, well, morphisms from y to z times morphisms from x to y to morphisms from x to z is biadditive, which is a bit like bilinear, except, well, just for abelian groups. And then we have a couple of more technical requirements. For example, we need to have finite products and finite coproducts. and they actually need to be the same. Then it needs to have an initial object. Then we need to have kernels and co-kernels, which in this case are just equalizers and co-equalizers with the distinguished zero element of the morphism group. And we need to have, what sort of amounts to the homomorphism theorem, meaning that epimorphisms and monomorphisms sort of factor through kernels and co-kernels. These are sort of technical conditions. And the main takeaway is that it is abelian if the Hom sets are abelian groups and the composition sort of preserves that property. And, well, it shouldn't surprise you to learn that all of these are actually abelian categories. But it turns out we have even more. Well, if we hone in on these two, because here we have not only addition, but we also have this scaling operation by the field k. Maybe we can incorporate that into a very specific kind of category. And this is exactly what we're doing. An abelian category. C is called k-linear, where k is a field. If, well, we already have that it's abelian, so it has to satisfy, obviously all of these conditions, but in particular it has to satisfy these three more technical conditions here. But in addition we need that for all objects x and y, the set of morphisms is not only an abelian group, but is a k-vector space. And then we also have a condition on the composition, and we want the composition to be not only bi-additive, but in fact k-bilinear. And that's it. And if you look at the category of k-vector spaces, then it indeed turns out that the homomorphisms between k-vector spaces, you can add them, you can scale them, and the composition is bilinear. Now we can do something a bit more funky, because, well, we can specialize this to a particular class of vector spaces. So a k-linear category C is called graded, or more properly Z graded, if, well, all of the Hom spaces are not only k-vector spaces, but graded k-vector spaces. What does that mean? It means usually we also write it with like a fat dot there, that we can decompose it as the direct sum of, well, Z many morphism spaces that are each called sort of morphisms of degree n. And, well, that is our condition on the morphism spaces. Now we also need a condition, of course, on the composition, and we want the composition to, well, sort of preserve the grading. What does that mean? It means if f is a morphism of degree n from y to z, and G is a morphism of degree m from x to y, then f after G is a morphism, well, obviously from x to z, but now the degrees add, and we have that this is of degree n plus m. And finally, a graded k-linear category C is called DG, or a DG category, where DG stands for differential graded, if all of the Hom spaces are also equipped with a map. So for all x and y in C, there's a map D, or there's a distinguished map D that goes from the morphisms between x and y to, well, the morphisms between x and y, satisfying a couple of conditions, namely, firstly, d squared is equal to 0, then d is of degree 1, meaning that if f is a morphism of degree n, then df is a morphism of degree n plus 1. And lastly, its interaction with composition. So if f is a morphism of degree n between y and z, and g is a morphism of degree m between x and y, then we have d of the composition f after g is equal to df after g plus minus 1 to the power of n, which is the degree of f after dg. And this last bit here is often referred to as the Leibniz rule, meaning that the d sort of behaves like a differential operator. Then this is sort of like the product rule, or some product rule-like rule. And while these definitions seem sort of ad hoc, there is actually an overarching framework, which is called the study of enriched categories, where we are just requiring that our Hom sets sort of lie in some monoidal category, and that then the composition is a map where we have the tensor product here. But since we have these technical extra conditions, what we defined here are actually more than just categories enriched in, well, the category AB, or k-vect, or graded k-vect, or DG k-vect, but actually a bit more.